In this lesson, we are going to discuss about the mighty RSA, one of the most important algorithm when it comes to cryptography and digital connected security in general. We'll start with a small puzzle which is common for RSA and Diffie-Hellman, which we will discuss later. And then on, we'll get into some mathematics, because understanding RSA with analogies is not very practical. We have to get into maths. We used analogy to understand hashing as well as encryption, the symmetric encryption. They are simple concepts at the end of the day. There are proper analogies that are available, like percentage, shuffling, etc. in the case of hashing and encryption respectively. But in the case of RSA, it is not that practical. So we have to get into some proper mathematics, some prime number factorization rules and things like that. And because of that reason, there is a little more difficulty to this particular chapter. Take your breaks and refer anything which you need and ask questions. So let's get into RSA. So RSA is the asymmetric cryptography. So I'll be synonymously using RSA, PKI, public key infrastructure. It's all different things actually. RSA is an algorithm. It's more of a infrastructure and a lot of other things related to it. But I'll be synonymously using all these every now and then. But essentially it conveys to the point that there are two different keys instead of one key. That's the whole idea about it. Also, I may be using asymmetric cryptography. We'll see this as well. The previous one was symmetric cryptography, where there is only one key for encoding or encrypting and decrypting. But in this case, there are two keys. One is the public key, which is known to everyone for encrypting, and decryption is done using a different key, a private key, which is a secret key. Unfortunately, the problem here to teach this thing is there is no simple example you can provide to explain the RSA algorithm. For example, in the case we have used a Moore's law operator for the hashing, simple hashing, although it is weak and not very useful, we were able to convey the concept using that. In the case of symmetric encryption, we simply use addition. But from a teaching perspective, if you use such kind of examples, it's not going to point to the actual concept. So we need to have certain amount of a rigor in this particular lesson. In fact, there'll be two lessons in this training which will have certain amount of rigor. One is this one, which you're watching. Another one will be coming up shortly when we explain so-called second pillar of the security, which are some of the bits in the CPU and the usage of it by the operating system. So this lesson is going to be a little long and bit a rigor. Take your breaks and pay attention, all that kind of things. It's going to be a little dry and probably a little rigor, number theory and all those kind of things we are going to discuss. To start with, I'll give you a puzzle. So the puzzle is, you have a secret object right here. There is a secret object right here. And here we have Alice. Alice is having a secret object with her, and she wants to transfer that secret object in a secured box. So she's going to put that in a box. So this is the box where she's going to put the secured object, and she need to lock this particular box. She is going to have a key. So this is the key Alice is having. This key can be a number, but the condition is that she need to transfer this particular object to a person called Bob right here. So Bob is in a different location. So he needs this particular object, and Alice want to give this particular object to Bob, and only to Bob. There is Eve in the middle. Eve is there in the middle. Eve is trying to access this particular thing right here. She is interested in this particular object right here. Let me draw that in a different color. So this is the red arrow going here, which is the axis of Eve. Now the puzzle is, how does Alice transfer this box, this secured box, without transferring this key to Bob? So Alice has a key. She doesn't want to transfer that key by any means. The reason is, if she transfers this key to Bob, this Eve, so this is Eve, this is Alice, and this is Bob. So if Alice is transferring the key, Eve can capture that key and unlock this particular object and take this object, and Eve can take that object. Bob will get a different object, or Eve can tamper with the object. So Alice doesn't want to transfer their key. So what is the solution? So your task as a puzzle solver is to design a lock such that the lock is locked while the transfer is happening through this transport mechanism, whatever it is, where Eve has access. But the lock cannot be opened by Eve by any mechanism. But Bob right here should be able to open it without this key. And he should be able to retrieve or keep things inside the box. That's the idea. So how do we solve this puzzle? So solution is to have two different keys and find out a special lock which can open with two different keys. So suppose we have a number lock right here. So number lock, let's say it's a 3-digit number lock. Number lock is easier to explain. And it opens at two different numbers. One, the first key is say 1, 2. So that is the key of Alice, 1, 2, 3. The other number which opens is 7, 8, 9. And that is a key Bob is having, 7, 8, 9. That is Bob's key. Either of these numbers will open this particular lock. This can be a very big number, like a 256 bits or 512 bits. In fact, these days the RSA keys are 4K keys are being used in production. We'll see such kind of things when we do the practical, but for the time being, this is just a 3-digit number. By the way, we are not explaining RSA algorithm exactly as it is. We are just getting a feel of it. The solution to this puzzle is not RSA algorithm. RSA algorithm is way more complicated than this. It is just getting a feel of how to transfer securely without the key being transferred to the other party. That's all this puzzle is about. Now, coming back to the puzzle, we have a number lock here opens at two different numbers. The first number or first key is 1, 2, 3. The second key is 7, 8, 9. And the first key is known to Alice. The second key is known to only to Bob. The first key is known only to Alice. The 1, 2, 3 is known only to Alice. Not to Bob, not to Eve, not to anyone else. The second key opens that lock is known to Bob. It is not known to Eve or Alice. Now, what is the mechanism we are going to do? Now that we have the lock is designed, what is next? Alice can put her thing into the box. After opening the box with this particular key combination, 1, 2, 3, that's her password or the key for the lock. She opened the box and put her things inside, the secret stuff she wants to share. So that is what is green stuff inside the box. Now she changes the key combination to 1, 1, 1, and Eve is getting the box. She's trying all kind of different things, but she doesn't have either this combination or this combination. So she's not able to open the box. Now Bob gets it. Bob gets this particular lock right here. He also don't have this 1, 2, 3 combination to open the lock, but he has another way to open the lock. He has a different key combination, 7, 8, 9, and he's gonna open that box using this second key combination, and he takes the things out of it. As you can see, without transferring the key, two different parties are able to communicate with two different keys. Kind of this is what happens in the RSA. In fact, this puzzle is more complicated than this. I have simplified this particular puzzle. The original puzzle is Alice lock with her key, send it to Bob. Bob locks with his key and send it to Alice. Alice unlock with her key, put the things, send it back to Bob, and Bob unlocks with his key and take the things out. It's a little more involved and there are a little more implications, but I want to make things simple for this training. So I have simplified the puzzle. In case if you have heard this puzzle before, I just wanted to put it out there. But the idea remains almost similar, while the original puzzle has a slightly different intention and objective. It's a protocol by itself. Now, the solution to not transferring the key over the transport is to have two different keys. Now, how do we implement it? So mathematically, how we can represent. Let me erase this and discuss about that. So what we are going to discuss is something called integer factorization problem, which is the backbone of public key infrastructure or RSA algorithm. Now we are going to discuss some technical things, mathematical things. Not very difficult, but you will have some of the questions. I will mention the questions as well as we progress. So integer factorization problem. So idea is very simple. We have 2 into 5 equal to 10. Both 2 and 5 are prime numbers. So we multiplied two prime numbers and we got an integer. The theory is that, at least as of now, we have not found any easy mechanism to factorize this 10 into 2 and 5, because 2 and 5 are prime numbers. Suppose if this 2 is a huge prime number, very big prime number, like a prime number with 1,000 digits. Another big prime number here with 1,000 digits, 2 and 5 in place of 2 and 5. And we multiplied it and we got another huge number here, which is a very big number because we have multiplied 2,000 digits. Now factorizing or finding out that two numbers from this big number is computationally impossible as of now. Being said that there are quantum computing, Shor's algorithm and things like that for integer factorization is there, which is slightly out of our discussion as of now, which can do certain things related to that, but that's out of our scope. By normal computing mechanisms, we cannot factorize an integer which is big and a multiple of two big prime numbers. So let's say the prime number is P and Q, big prime numbers, and PQ is the number we have. The difficulty of finding P and Q given PQ, P into Q, is what we call the integer factorization problem. And this is what we are going to use for public key infrastructure. So to summarize the integer factorization problem, at the end of the day, if you have two very large prime number, and if you multiply that two prime numbers and getting a bigger number, which is bigger than both the large prime numbers, to factorize or finding that multiples, there is no easy mechanism. By the way, what is a prime number? If you're new to prime numbers are very important factor when it comes to cryptography. In fact, some other part of the cryptography also uses prime numbers. For example, 2 is a prime number, 3, then 5, 7, 9 is a prime number? No, 9 is not a prime number. 11 is a prime number, 13, 17, and so on. The reason why it is prime number, because it has only two factors, 1 and 2. In this case, 1 and 3. How about 4? Why 4 is not a prime number? Because 4 we can write, say 4, we can write 2 into 2, which is 2 prime numbers. There are multiple of prime numbers. We can write non-prime numbers as multiple of other prime numbers. 5 again, 1 and 5. 7, 1 and 7. Why 8 is not a prime number or 6 is not a prime number? Because we can write 6 as 3 into 2 and 8 as 2 into 4 or 2 into 2 into 2. Like that, 11, 13 and 17. If you want to read more about prime numbers, there are so many interesting problems in prime number. The Riemannian hypothesis, then a lot of other interesting problems are there in prime numbers. One thing with prime number is that it has been proven that there are infinite number of prime numbers. There is no last prime number. It has been proven that there are infinite amount of prime numbers. So we can find any arbitrary large prime numbers, P and Q, and we can multiply those two numbers and we get a big number. And there is no easy way to find out P and Q out of this result we get after multiplication. So that is the integer factorization problem. Now, for putting this use in cryptography, there is a bit more work involved, which is what we are going to do. And like I was mentioning, it is not going to be straightforward. There are a couple of different operations to be done to achieve it. First of all, we need to come up with some goals, what we are trying to achieve before we get into it. So in this case, what I'm going to do is I'm going to go to something like Microsoft Copilot or ChatGPT or any LLM, even Google for that matter. And I'm going to take an example of an RSA algorithm and we will go from there. So if you are doing this yourself, you can find your own favorite search engine, RSA sample. This is Microsoft Copilot I'm using. So we are getting an example here. As you can see, 2 prime numbers has been selected, P and Q, and some operations are being performed on it. Now let's try to understand what is the goal before we start the analysis of it. So the goal here is we have 2 prime numbers, P and Q, like I mentioned. Let's say 3 and 11, both are prime numbers. Now we are going to have a message M. So there is a message M we are going to have. And this is the message right here, the M. We are going to encrypt that message. What is encryption? We are going to perform some operation using this P and Q, these prime numbers, these 2 prime numbers. We are going to perform some operation on M such that M is not obtainable from the ciphertext C. We have seen that in the symmetric encryption case. We are going to perform some operation in M. And later, with the help of a different number, which is connected to P and Q, in fact, everything is going to get connected to P and Q, we will be able to retrieve M. So the encryption process is this and decryption process is this. So the ciphertext C is calculated with the help of M. M to the power E, that is the ciphertext we are having. Mod N, we don't know what is N and E, they are unknown to us. M is the number which we want to encrypt. You need to pay attention here. M is the number we want to encrypt. This is a secret number. It can be anything. It can be your bank account, anything. So that is the number we want to keep it secret. And E and N, those are the 2 numbers we are using. E and N. We don't know what is it now. Those are the numbers we are using to produce the ciphertext C. And this is the calculation we are performing. So 4 raised to 3 mod 33. In this case, the E equal to 3 and N equal to 33. We are getting 64 mod 33 equal to 31. So this is the ciphertext. This is visible to the whole world. This 31 is visible to the whole world. And we know that the 4 is hidden inside this 31 somehow. The 4 is encrypted within this 31. This 31 is the public encrypted representation of number 4. But no one knows that. No one knows about 4. No one has to know about 4. That's the idea. And what are the numbers used? Of course, the M is used, which is the 4 itself. Then E and N. What is N? N is 33 and E is 3. We don't know how it got obtained. That is what explained here. If you want, you can have a pause and look. Not a big deal. We'll get into it. But for the time being, E and N is used. Now we have 31 and we need to find 4 from the 31. That process is called decryption. Now, what is the formula for finding M from C? To C is here. The formula is C raised to D. There is another number has come up. Mod N. This is common. Mod N. That is common. In both encryption and decryption, N is common. As you can see, N is common. But D, there is another number D right here. This is a crux of this discussion, everyone. So pay attention. So D is a number which is not here. We used E, but D is not there. D is used for decryption. There is a different number, part of the private key. Very important. C raised to D mod N equal to M. In this case, 31 raised to 7. D is 7 in our case. 31 raised to 7 mod 33. is a pretty big number. If you want to put it in a calculator or something, you can try that. We'll see if you can use some calculators to find some of these numbers, but when you get bigger numbers, it's impossible to calculate the complete result of this particular exponent right here. But there are ways to compute. We'll discuss that as well in the end, but let's focus on the calculation right now. Ciphertext raised to d, which is part of the private key, mod 33, which is n, equal to 4. So we got the 4. So this is the crux of this discussion. Now all we need to do is to find out the calculation tricks to calculate E, N, and D. That's all we are going to do next to understand this. So we started with P and Q. Where is that P and Q? In fact, all these numbers are developed from that P and Q, right? So let's consider what is N. N is very straightforward. N is PQ. Remember that product we were discussing? N is PQ. And N is part of the public key. Everyone knows about N. No one knows about P or Q. Secret. No one knows about P and Q. Now we are calculating another number, P minus 1 into Q minus 1, which is 2 into 10, which is 20. Now we got N, which is PQ. Now we need to find out E, or public exponent E, which is part of the public key. This is part of the public key. Public key is basically E and N. That's the public key. The formula for, or the technique for finding the public exponent is 1 less than E less than this particular value we have calculated right here, which is 20. And so the value of E should be within the range of 20 and 1, as well as there is one more condition for E, is it should be co-prime with 20. What that means? Co-prime with 20. So what is co-prime? So this is the definition of co-prime. The number 3, the two integers A and B are co-prime, or relatively prime, or mutually prime, if the only positive integer that is a divisor of both of them is 1. So basically, they should not have any common divisors other than 1 and itself. So for example, 9 and 4 are co-primes. Why? Because they don't have any common divisors. They are co-primes. So the greatest common divisor is 1 in the case of 9 and 4. 2 and 3 are co-primes. They are actually primes. Co-primes can be primes as well. 4 and 6 are not co-primes. They have a common divisor, which is 2. So they are not co-primes. So that is the definition of co-prime. No common factors. If you want, you can read more about it. So in this case, they have chosen E, which is a prime number anyway, as a co-prime. For example, prime numbers are always co-primes. They could have chosen something like 3, 5. 4 is not co-prime with 20. Why? Because 2 is a common factor. 6 is not a co-prime with 20 because 2 is a common factor. 7 is a prime as well as co-prime to 20. Another example is 9. 9 is a co-prime to 20 because there is no common factors. 3 into 3 is 9. 2 into 2 into 5, that is 20. So that is the explanation of public exponent, or how the public exponent is calculated. Now the final one is the D, which is part of the private key, how it is calculated. D is called modular inverse of this particular number, E modulo phi n. This is called the Euler's tangent function. I'm assuming I'm pronouncing it correctly. So what is the concept of modular inverse? Basically, it needs to satisfy this particular equation. D into E equal to 1 mod phi n, or 1 mod 20 in this case. To expand this, I'm going to write another prompt here. Explain the calculation of D. So it is giving us similar explanation which it has given before, along with some calculation and how it is using something called Euclidean algorithm to calculate it. We don't have to get into the details of the efficient way to calculate it. But in our case, what we need to understand is that it satisfies this particular equation right here. We can pay attention to just this one equation right here. So this one is exactly this particular one right here. And this 20 is our 20 before, which is the phi n, and 3 and 7. We already know what is 3, which is our e, which is the value we got it here in this step right here, the public exponent. Now we need to find out such a value for d that when we do this, we get 1. So mod 20, so this value mod 20 should be 1. So that's the idea here. The reason for this 3 hyphens here instead of 2, which is equal to, is that there could be other numbers other than 7 which satisfies this particular equation, because it is a mod operation. We have seen mod operation which is focusing on the remainder of the division. Remainder keeps repeating. Because of that reason, this equation has multiple solutions, and one solution is 7. That's why this 3 hyphens here to mention that particular point. Now, how do we get the d? By solving this particular equation. There could be multiple different values for d which satisfy this. Like I mentioned, in our case, we got 7 because 7 into 3 minus 20 equal to 1. That is the equation we are trying to solve here. So we got everything we needed. We got d, e, and n. Now, what is the public key? What is the information or the key which we are using to encrypt the information? Which is e and n. We have seen this formula to encrypt. How do we encrypt? M, which is a message, raised to e, which is 3 in this case, and mod n. We are taking the modulus. We are interested only in the remainder. If you have any confusion on what is mod, please refer to the hashing session. We are taking the remainder after dividing with this number. We are interested in the remainder. What is remaining? Not interested in the quotient. That is mod is all about. M raised to e, 4 raised to 3, mod n, which is 33. This is n, not phi n. This is n. That is the encryption, and we get this particular value right here. Now, how do we get it back? How do we get 4 from 31? That is the secret. That is a crux. And for that, we need to use the private key, which is different from public key. The d which we calculated is part of the private key. So in this case, d is 7. We have seen that 7 is the d. And the formula for calculating is c raised to d mod n. C raised to d mod n. That's a formula for calculating. So c is the ciphertext, which is 31. We got it here. And raised to d mod n, we get the message like this. Again, we are doing the mod. We are interested in the remainder. Now, the big question is, what if the attacker can calculate d from all the other numbers? Let's think about that possibility. Because if d is known to the attacker or someone outside, the whole thing is a waste of time. It is hacked on the day one. Now, we need to understand the possibility of finding out d, the calculation of d. Let's see what are the things we are using to calculate d. First of all, we are using e to calculate d. E is required to calculate d. As you can see here, e is used. Another thing we are using is phi n. Is it public? No, it is not public. But e is public though. Everyone knows e, which is used to calculate d. E is public, but this is not public. But n is public. Can we calculate phi n with n? Then we are in trouble. Are we in trouble? No, we are not in trouble. the whole world will be in trouble if that is possible. Why it is not possible? Because of this right here. Because phi n equal to p minus 1 and q minus 1. Does anyone know what is p and q? No one knows what is p and q. Why? Because n cannot be factorized easily to p and q. Why? Because of the integer factorization problem. If you want, you can repeat this part of the video if you're really keen to understand what I just said. Either way, I'm going to repeat it. In fact, you may have to watch this particular thing probably 10 times or 12 times or how many times you want to understand most of it. Probably you need to do your own research as well. So many things I'm skipping. For example, how this formula is coming into the picture. It's all deep mathematical inputs, which we don't want to delve in. We are taking these formulas as it is. These two formulas has a lot of maths involved. Number theory, left, right, and center. The derivation of this particular part. But otherwise, what our concern here is that can we calculate D from E and rest of the available thing, especially N and phi n, which looks very close to N. And the calculation looks very similar. P minus 1 into Q minus 1. That is phi n. If this is out, our private key can be calculated. And as a result, the message can be decrypted as well by the attacker. Now, the reason why we cannot create this is we don't know what is P and Q because of integer factorization problem. Now, it looks straightforward in this small example right here. But in the real world, these numbers are at least 256 bits. The key is these days 4K bits. It's like 4K is like almost 100, more than 100 digits, I guess, when you calculate what is 4K. But the key length used these days in production scenarios are 4K keys. Recently, I'm working on a project to migrate all the 2K keys to 4K. That's a project which I'm working in my consultancy side as we speak to make it more secure. All the 2K keys are changing to 4K. It is not that 2K is very insecure or anything like that, but just people are using 4K as the accepted standard, which means these numbers are thousands of digits. It's not even millions and billions, it's all quadrillions and quadrillions. So big numbers we are using. There is no way to calculate otherwise unless you have an algorithm to do it, which is not found as of today. Integer factorization problem is what we are talking here. These are all very big numbers. Look simple in this simple scenario. 3 into 11 equal to 33. Finding 3 and 11 from 33 is the problem we are talking about. It is looking simple in this example, but in very big numbers, there is no easy way to do it. So that is the summary of RSA algorithm. In fact, we have gone through the 90% or the 100% of the required details. All we have to know is that the private key and the public key, they are different. And there is no way to calculate the private key from the public key unless you factorize this particular number, which is not possible. We have seen that. If you have any question on that, either you ask me or watch this video again. Do more research. You can ask something like ChatGPT more questions. For example, how do we get this formula? You can ask that thing. It'll give you some more explanation. You can keep asking or keep refer to some other documents as well. This is not really important for our training purpose. We are not into cryptography or number theory. It's not even cryptography we are talking about number theory. Now, one thing I would like to talk here is that before we go, so these calculations right here can be very, very tricky things. For example, these numbers right here. So let's see a better example to demonstrate the point which I'm trying to convey here. Please give a bigger number example. So we are dealing with very small numbers, 7 and 3, which doesn't prove our point. Now it has given a fairly big number right here. Now it is not going to stay in our head. This is gonna blow out pretty quick. And n is pretty big number again. This is another big number. Now what I wanted to show you is that the D is also pretty big. As you can see here, it's blown out pretty quick. The private key is this and public key is this. Now let me show you what I wanted to show. That is this particular thing right here. You see 89 raised to 17. It's a very hard calculation. 89 raised to 17 is a huge number. None of the calculators we know can calculate this. But what I wanted to tell you is that there are shortcuts to do that, to find out the whole result without really calculating the full 89 raised to 17. There are methods, there are numerical algorithms, pure mathematical algorithms available to calculate this whole thing without knowing what this number is. Let me show you the decryption part. The decryption part is even more crazy. 2201 raised to 2753. This is like a ridiculously high number. There is no computation on earth can perform this in my view. And after computing that, you need to mod it with this number as well. So how do we calculate this? Same thing. We have other mechanism to calculate this, other algorithms. We don't have to multiply this number this many times and divide it with this number to get the remainder. All we are interested in, remainder. We are not going into the details of how this is getting calculated, but all you have to know is this is all being baked into the solution. So people has thought about how all these things could be calculated. These are some of the things which is hidden in the thing we just explained. So that way we don't have the 100% rigor which we don't need when we explained the whole flow. So coming back to our original discussion, long story short, we have a different encryption key and different decryption key, and the decryption key is secret and no way to find from the public key. That is the summary. We have not understood anything, just keep these two things in mind. Encryption is one thing, decryption is another thing. And the whole world depends on this one particular fact. If this goes wrong, you can see hundreds of things goes wrong in the world right now. It's that important. So that was a toy example. All 61, 53, and all these are toy stuff. Now let's see a real stuff. What we are going to do is we are going to do encryption and decryption using OpenSSL on a real world example or real world private key and public key. That's what we are going to do next using OpenSSL. So to summarize what we are going to do using OpenSSL, first we are going to create the private key, this particular number right here. Then we are going to create the public key, which is these two numbers right here, and then do an encryption of a message like we did before and decryption of that message using the private key. Can we decrypt the message using the public key? No way. Absolutely no way to decrypt the message using public key. Only encryption can be done using public key. Very, very important point. There is no way to decrypt the message without the private key, without this particular number right here. That's the whole point. Let's do that. So I have created a folder for the keys. So the command is OpenSSL gen RSA. That's the command, the OpenSSL command we need. Then out private key .pem. Normally it is in PEM format. Then the length of the key 1024. I'm going to give it 1024. This is the 4K 2K thingy I was talking. So this is 1K. The length of the key will be 1K in this. We don't need too many big key for the time being, but you can perform any number you want, depends on your requirement. In this case, I'm going to perform 1K or 1024. So again, the command I'm going to repeat: OpenSSL gen RSA out, then the file name in which the private key will be coming. So this is the private key we are generating, not the public key. Let's see the command works. The command worked. Let's see the key in Notepad. Notepad private key.perm, and this is how the private key looks. As you can see, this is a pretty big number right here. There's actually a number. There's an encoded number. There is way to get those two numbers we saw in a slightly different format at least, but this is pretty big information right here. As you can see, any brute force attack towards a password like this, literally impossible. And let's see the 4K key. I'll generate a 4K key just for showing how big it is. Underscore 4K, and I'll perform 4K here, 4098, and I'm going to open up that in Notepad, underscore 4K. As you can see, this is pretty big, 4 times big as the previous one. Again, it is one big number right here. We have the 4K private key. Let's continue generating the public key. So I'm going to close this. We'll be using the small key for our purpose. So there is a little more involved creating the public key. First of all, we need a private key to create the public key. OpenSSL RSA, instead of gen RSA, it is RSA in the corresponding private key.perm, out the public key.perm. So this is the command. Then we need to mention the format in which we need the public key. Out form equal to PEM format. So PEM format is nothing but a text format, which normally the certificate and keys these days are mentioned. PEM format is just a text format. We already seen the PEM format. We'll see a lot of PEM format throughout this training while we deal with certificates. Now we need one more argument to tell it that we need a public key out. So hyphen pub out. So that's the full command. So OpenSSL RSA in private key. We need to input the private key to generate the public key. Out, this is the output we are going to get, the format of the output, and then the pub out. Hopefully this command will work. Let's see. Looks like it worked. Writing the RSA key. Let's see the public key. Okay, it doesn't work. Again, we need Notepad public key.perm. So public key is pretty small compared to private key. So this is the public key. So PEM format has this kind of header and footer start. If you see this kind of things, it means that it is PEM format. It's very readable that way. It is supposed to be text. The PEM format is text at the end of the day, encoded text. So we got the private key and public key. Next is encryption and decryption. First, we need to create a message to encrypt the secret message. So let's do that. Notepad secret.txt. So this is the secret message we are going to create. This is a big private key or key for symmetric encryption. Some message we have. I'm going to save that file. And now next you see encryption command. Again, OpenSSL. Now the command is pkeyutl. So that is the command we'll be using to encrypt encrypt in key. So which key we are going to use to encrypt? The public key. So public key we are going to use to encrypt, and in, which is the message we are going to encrypt, secret.txt. That is the message we are going to encrypt, and out ciphertext.txt. So we need an additional hyphen in all these arguments. There is an additional hyphen here, here, and here. Keep an attention to those things if you are doing it by yourself. There is one more argument we need here is pub in to show that public key in. Pub in. So this should work. Let's try it out. we got something. Let's see if we got something in the ciphertext. Notepad, ciphertext.txt. At least the file is created. The file was not there. As you can see, the file is very garbled. It's not a very friendly file. As you can see, this is not a text file. It is a binary file. So this is the encrypted file. It is not because of it is encrypted. It is showing like this. It is because it is a binary file. It is not a text file. That's why we are getting all this extra characters and things like that. I'm going to close this because we can't see anything useful out of it. At least the file is created. Now next thing is to check whether we can successfully decrypt that file. What is a key we are going to use for decryption? Public or private? Think private key. We are going to use private key for decryption, and we cannot, again I'm going to repeat, we cannot decrypt the message using public key. Without the private key, we cannot decrypt this file. That's a whole point of this RSA or PKI infrastructure we are talking about. There is a whole lot of things running in the world because of this thing. So very, very important. Encryption is public key and decryption is private key. So let's try that. Now open SSL, pkutil, the same tool. This time it is decrypt the message. --in key. Which key we want? Private key .pam. In ciphertext, out message. Put it decrypted message .txt. Let's see if it works. If it is not working, we need to troubleshoot. Looks like something has worked. Now what I'm going to do, I'm going to notepad decrypted message, and we got our original message. So very important session. It is very long and tedious as well. I hope you had the patience to listen to what I'm saying right now till the end. We have gone through the RSA algorithm, the public key, private key infrastructure, very important from the security perspective, getting the root of this particular encryption standard or algorithm. Everything from email to phone calls to bank accounts to military defense, everything depends on this one single thing we are discussing right now. If this is broken, we will not see the world as it is today. When you watch a YouTube video or Instagram or Facebook, you should remember about RSA algorithm, public key infrastructure. Now we have almost covered the first pillar. Now we need to understand the different technologies built on top of this. But for the time being, we are good. So this is the RSA. Watch this particular session a couple of times because this is a difficult one. Make sure that you read additional materials if required, especially on the mathematical side of the things, number theory, etc. But that is not really required for us to proceed. Even if you didn't understand that particular calculation we did, we are good to go. All we need to understand is what is public key and private key. But if you want to pay attention and do those calculations, I really recommend that. So we have seen the nuts and bolts of RSA. We have seen some examples as well. Now throughout the connected security part, we will be using it. Yet again, I want to mention that please refer to other documentation, ask questions because it was a tough topic. In fact, we will discuss Diffie-Hellman, which is very similar to RSA, but there is a subtle difference, important difference. We'll discuss that as well on the way. But feel free to watch this lesson again, as well as in case if you're finding difficulty, always ask me questions, review the video again, take your breaks. All the basics is needed for this particular lesson because of the complexity. Thank you very much and see you in the next.